Hey there, and welcome back to our Examify IGCSE physics course. In this video, we will be diving into Unit 2, Thermal Physics, where we explore how heat, particles, and energy all work together. This isn't just about temperature, it's about understanding the hidden world of particles and how they behave under different conditions. So let's go! Everything around you, solids, liquids, and gases, is composed of tiny particles, whether they may be atoms, molecules, or ions. The kinetic particle model is a crucial framework that aids us in understanding the behavior and properties of these particles under various conditions. In a solid, particles are arranged in a closely packed, fixed structure where they can only vibrate in place. This arrangement gives the solids their definite shape and volume. The strong intermolecular forces hold the particles tightly together, preventing them from moving freely. In a liquid, the particles are still close together but possess enough energy to move past one another, allowing liquids to take the shape of their container while maintaining a fixed volume. The intermolecular forces are weaker than in solids, facilitating this movement and creating fluidity. In a gas, particles are much further apart and move independently of one another. The energy of the gas particles is significantly higher, enabling them to overcome the intermolecular attractions and spread out to fill any space they occupy. This results in gases having neither a definite volume nor a definite shape. When substances undergo a change of state, such as melting, boiling, or freezing, there is an interesting phenomenon. The temperature remains constant during the phase change. This occurs because the energy supplied to the substance is utilized to break or form intermolecular bonds between particles rather than increasing the temperature. For example, in pure water, the melting point is precisely 0 degrees Celsius, and the boiling point is 100 degrees Celsius at standard atmospheric pressure. During these phase transitions, the heat curve flattens, indicating that while energy is being added or removed, it is not increasing the temperature, but is instead facilitating the transition between states. Next up, we have evaporation and boiling. So what's exactly the difference between the two? Evaporation occurs only at the surface of a liquid and can take place at any temperature. It is generally a slow process as only the most energetic particles at the surface escape into the gas phase. Boiling, on the other hand, occurs throughout the entire liquid when it reaches the boiling point. It's a rapid process characterized by the formation of bubbles within the liquid as vapor forms. An interesting aspect of evaporation is its cooling effect. As the fast-moving, most energetic particles escape, the average kinetic energy of the remaining liquid decreases, leading to a drop in temperature. To enhance evaporation, consider increasing the surface area, for example, by spreading a liquid in a shallow disk, raising the temperature, which gives the particles more energy, or ensuring the air is moving, which disperses the vapor that forms above the liquid. Have you ever observed dust particles dancing in a beam of sunlight? This phenomenon is called Brownian motion, a compelling demonstration of the random motion and collisions of microscopic particles. This observation provided one of the earliest pieces of evidence for the existence of atoms and molecules, long before scientists had the technology to visualize them directly. Here, the smoke particle is hit by fast-moving air molecules from one side, then the other. This leads to the rapid change in direction of the smoke particle, resulting in its random motion. And now, let's delve into the behavior of gases. As the temperature of gas increases, its particles gain energy and move faster. This increased movement can lead to an increase in pressure or volume, depending on what constraints are applied to the gas. The fundamental equations that describe gas behavior are Boyle's law. So this states that the product of pressure and volume is constant when the temperature is kept constant. The most important formula to remember here is P1V1 equals to P2V2. That is, the product of the initial pressure and initial volume equals to the product of the final pressure and the final volume. The term absolute zero refers to the theoretical lowest possible temperature, where all particle motion ceases, occurring at negative 273 degrees Celsius or 0 Kelvin. To convert temperatures from Celsius to Kelvin, you can use the following formula. Temperature in Kelvin equals temperature in degrees Celsius plus 273. As we continue with thermal physics, we will now be moving into thermal properties. The first phenomenon is thermal expansion. When substances are subjected to an increase in temperature, they undergo a phenomenon known as thermal expansion. This occurs because the particles within the substance begin to vibrate more intensely, which causes them to occupy a greater volume due to the increasing kinetic energy associated with the higher temperatures. The properties that affect the amount of thermal expansion are as follows. Number 1 is the state. Gases expand more than liquids. Liquids expand more than solids. This is because gases have weaker bonds than liquids, and liquids are weaker than solids. The second one is temperature. The higher the temperature, the more a substance expands. The last one is initial volume. The higher the volume, the more the substance expands. Now let's move on to some applications of thermal expansion. One of it is the thermometers. Thermometers use thermal expansion to show the temperature. Second is the fitting rings over rods. This is done by heating iron rings to make them expand so they can fit onto wheels. Last one is bimetallic strips. These are strips made of two different solids, which are stuck together. When heated, one expands more than the other. These are used mainly in thermostats and fire alarms. To understand thermal properties more effectively, it's important to differentiate between two key concepts: temperature and internal energy. Temperature is defined as the measure of the average kinetic energy of the particles in a substance. It essentially indicates how fast the particles are moving. Higher temperatures correspond to greater kinetic energy. Internal energy, on the other hand, refers to the total energy contained within a substance particles. This includes not only the kinetic energy arising from their motion, but also the potential energy related to their positions and interactions with one another. Coming up is another key concept to remember: specific heat capacity. Different materials have varying abilities to absorb heat, which is quantified by the specific heat capacity of a substance. This term refers to the amount of energy required to raise the temperature of 1 kilogram of a material by 1 degree Celsius. The relationship is expressed in the formula change in E equals mc change in T. where change in E represents the energy change, m is the mass of the substance, C is the specific heat capacity of the substance, and change in T is the change in temperature. Water, for example, is known for its high specific heat capacity. It's approximately 4.18 joules per gram degree Celsius. This means it requires a significant amount of energy to increase its temperature, which is why it is commonly used in applications like car radiators and climate control systems. The high specific heat capacity of water helps to moderate temperature changes in the environment, making it an essential component in thermal regulation. In this chapter, we will explore the mechanisms by which heat travels, which occur primarily through three processes: conduction, convection, and radiation. Conduction is the process of heat transfer that occurs in solids, particularly in metals due to their atomic structure and free electrons. When one end of a metal conductor, like a spoon, is placed in hot tea, the increased kinetic energy from the heated particles at the end spreads through particle-to-particle vibrations. The tightly packed atoms in the metal transmit this energy quickly, allowing heat to flow efficiently along the length of the spoon. In contrast, wood, a poor conductor of heat, has tightly bound molecules that do not allow energy transfer as efficiently, which is why a wooden spoon remains cool when placed in the same hot tea. Convection is the method of heat transfer that occurs in fluids, which includes both liquids and gases. When a fluid is heated, its molecules gain energy, causing them to move faster and become less dense. As the less dense, heated fluid rises, cooler, denser fluid moves downward to take its place, creating a continuous loop known as the convection current. This process not only transfers heat but also enables even heating to take place. Practical example of convection can be observed when using a kettle. As the water at the bottom heats, it rises to the surface, while cooler water descends, leading to a uniform increase in temperature across the entire volume of water. This principle is also crucial in natural phenomena such as weather patterns and ocean currents. The last method of heat transfer is known as radiation. Radiation is unique in that it does not require a medium or any particles to transfer the heat. Instead, it involves the emission of energy in the form of electromagnetic waves, specifically infrared radiation, which travels through the vacuum of space. This is how sun's energy reaches Earth, warming our planet. When these waves encounter an object, they can be absorbed, reflected, or transmitted depending on the object's surface properties. Dark, dull surfaces, such as asphalt, absorb radiation more effectively, leading to an increased temperatures upon exposure to sunlight. In contrast, shiny and reflective surfaces like aluminium foil bounce back much of the incoming radiation, which is why car dashboards can be extremely hot while the reflective surfaces remain relatively cool. Understanding radiation is essential, not only in everyday applications like cooking and heating, but also in installation technologies. When coming to radiation, there are two important experiments you need to remember for the IGCSE syllabus. The first one is the experiment to differentiate between good and bad emitters of infrared radiation. The steps for this are as follows. First, set up a cardboard box as shown in the picture, coating each side with a different color and texture, such as shiny white, shiny black, dull white, and dull black. Pour hot water into the container. Make sure the hot water is at the same initial temperature. Place a thermometer in front of each surface. The side in which the temperature increases the fastest will be the best emitter. That is here the dull black side. And then the side in which the temperature increases the slowest will be the worst emitter. This is the shiny white side. The next experiment is the experiment to distinguish between good and bad absorbers of infrared radiation. The steps for this experiment are as follows. The first step is to get 4 identical metal cans and paint each one with a different color. Fill each can with equal volumes of water at the same temperature and put a thermometer in each can. Place a heater in the middle of the cans and make sure that the distance between each can and the heater is equal for a fair comparison. Step 4. Turn on a heater and measure the temperature of each can at equal time intervals. Step 5. The can with the fastest temperature increase is the best absorber, and the slowest rate of temperature increase will be the worst absorber. And that's the end of Unit 2, Thermal Physics. In this unit, we have gone through from understanding the kinetic particle model to mastering how heat moves, how substances change state, and why temperature and internal energy are the same thing. We have seen how evaporation cools, how gases behave at different temperatures, and how conduction, convection, and radiation each play their role in transferring thermal energy. These ideas aren't just exam topics. They explain why bridges have expansion gaps, why ice floats, how your kettle works, and even how heat travels from the sun to earth. You have built the skills to connect microscopic particle movement to the big changes you see in the real world. So well done on completing this chapter. Take a moment to review your notes, and when you're ready, we will move on to the next unit where we explore the amazing world of waves.